Overview of NumPy. NumPy, which stands for Numerical Python, is a fundamental package for scientific computing in Python. It provides a high-performance multi-dimensional array object, various derived objects, such as masked arrays and matrices, and an assortment of routines for fast operations on arrays, including mathematical, logical, shape manipulation, sorting, selecting, I/O, discrete Fourier transforms, basic linear algebra, basic statistical operations, random simulation, and much more. NumPy is essential in the field of data science and analytics, as it offers the array data structure that's far more efficient for mathematical operations than native Python lists. The fact that it's written in C ensures that performance is highly optimized. Installing NumPy. NumPy is a powerful library for numerical computing in Python. Before using NumPy, you must install it. The most common method to install NumPy is using pip, which is the Python package installer. The provided command is used to install NumPy using pip, which is the package installer for Python. Once you run this command in your terminal for Mac Linux or command prompt PowerShell for Windows, pip will download and install the NumPy package along with its dependencies. After the installation is complete, you can import NumPy in your Python scripts using import NumPy. Importing NumPy library. To start using NumPy in a Python program, you first need to import the library. It's standard practice to import NumPy with the alias np, which allows you to access all of NumPy's functions, objects, and modules with a shortened prefix. The provided line of code imports the NumPy library and sets up np as an alias. Whenever you need to use a function from NumPy, you can prefix it with np instead of typing NumPy. This saves time and keeps your code cleaner and more consistent with the conventions used by the Python community. Understanding ndarrays, n-dimensional arrays. In NumPy, the primary data structure is the ndarray, which stands for n-dimensional array. It is a grid of values, all of the same type, indexed by a tuple of non-negative integers. The dimensions of the array are known as axes. The number of axes is its rank. Let's explore a basic ndarray creation and its attributes. In the provided code, we import the NumPy library and create a two-dimensional array, A, with two axes, rows and columns. We then print the array and its attributes. Ndim gives the number of dimensions, axes. Shape provides the dimensions of the array as a tuple, rows, columns. Size returns the total number of elements, and dtype shows the data type of the elements in the array. This shows how to initialize an ndarray and examine basic properties that describe its structure. Data types in NumPy. NumPy supports a much greater variety of numerical types than Python does. This comes in handy when you need more control over how data is stored in memory and on disk, especially for large datasets that require numerical computing optimizations. Understanding these data types is foundational for efficient NumPy programming. In the provided code, we import NumPy and create several arrays with different data types. A is an array of 32-bit integers. B is an array of 64-bit floating-point numbers. C is an array of 128-bit complex numbers. D is an array of Boolean values. And E is an array of strings. By specifying the D-type argument when creating the arrays, we're telling NumPy exactly what type of data we're storing. The print statements display the data type of each array, demonstrating how NumPy represents these types internally. Array attributes: shape, size, ndim, dtype. In NumPy, arrays have several basic attributes that describe their structure. Shape tells us the dimensions of the array, size gives the total count of elements, ndim reveals the number of dimensions, and dtype shows the data type of the array elements. In the code, a two-dimensional NumPy array R is created with shape 2, 3. rr.shape returns the array's current shape as a tuple, here 2, 3, which means the array has 2 rows and 3 columns. r.size returns the total number of elements in the array, which is 6. r.ndim gives the number of dimensions, which is 2 for this 2D array. r.dtype returns the data type of the elements, which is int64 on most 64-bit systems. This information is fundamental for understanding and manipulating arrays in NumPy. Creating arrays from lists and tuples. NumPy provides an easy way to create arrays from existing sequences like lists and tuples. This is done using the np.array function, which converts the input sequence into a NumPy array. This enables the performance benefits and functionalities of NumPy arrays while starting from familiar Python data structures. The code imports the NumPy library and then creates two arrays. The first array, list array, is created from a list of integers 1, 2, 3, 4, 5. The second array, tuple array, is made from a tuple of integers 10, 20, 30, 40, 50. The np.array function takes these sequences and converts them into NumPy arrays, which supports NumPy's array operations and methods. Using array-generating functions, arrange one's zeros linspace logspace. The NumPy.arrange function creates an array with evenly spaced values within a specified range. The code creates a 1D NumPy array, starting from 0 up to, but not including, 10 with a step of 2 between values. Thus, the array will contain 0, 2, 4, 6, 8. Creating identity matrices, I-identity. In linear algebra, an identity matrix is a square matrix with ones on the main diagonal and zeros elsewhere. NumPy provides two ways to create identity matrices, np.I and np.identity. The function np.I can create non-square matrices with ones on a diagonal, specified by the k parameter, while np.identity always returns a square identity matrix. The code above demonstrates the use of np.identity and np.I functions to create identity matrices. np.identity3 creates a 3x3 square matrix with ones on the main diagonal. np.I k=1 creates a 4x4 matrix with ones on the diagonal, one above the main diagonal, effectively shifting the diagonal up by one position. np.I can also create non-square matrices if a second dimension is provided, and the k parameter can be negative, which would place the diagonal below the main diagonal. The empty function. In NumPy, the empty function is used to create a new array of a given shape and type, without initializing entries. It is important to note that the empty function does not zero the elements of the array. Rather, it allocates the memory for the array, and any value that happens to already be in that memory will be the initial content. This is useful for efficiency when you plan to overwrite all elements anyway and care about performance. The above code uses np.empty to create an array with 3 rows and 2 columns of integers. Because np.empty does not initialize the array, the content of the array A is unpredictable and could be anything. It is effectively garbage values. When the array is printed, it might contain random numbers, and these numbers could be different each time the code runs. It is crucial to assign new values to all elements of an uninitialized array before using it in any computation to avoid unexpected results. Random number generation in arrays. NumPy provides utilities for random number generation through its numpy.random module. This module includes functions to generate arrays of random numbers from various statistical distributions. For example, numpy.random.rand can be used to create an array of specified shape with random samples from a uniform distribution over 0, 1, and numpy.random.randint can generate random integers. In the provided code, np.random.rand33 creates a 3x3 array of random floats between 0 and 1. Each number is drawn from a uniform distribution over the half-open interval 0, 1. On the other hand, np.random.randint 0, 100, 33 generates a 3x3 array of random integers where each integer is in the half-open interval 0, 100, meaning it can range from 0 to 99. These functions are useful for generating random data for simulations, examples, or for initializing parameters in algorithms. Array arithmetic addition, subtraction, multiplication, division. In NumPy, arrays allow for element-wise arithmetic operations, which means that standard arithmetic operations such as addition, subtraction, multiplication, and division can be performed on an element-by-element basis between arrays of equal size or between an array and a scalar. In the provided code, 2 NumPy arrays A and B are defined with 3 elements each. Various arithmetic operations are performed between these arrays. Addition of A and B gives a new array C, with each element being the sum of the corresponding elements in A and B. Subtraction gives array D with elements being the difference. Multiplication gives array E with each element being the product. And division gives array F with each element being the quotient of the corresponding elements. The operations are performed element-wise, and the results are printed to the console. Broadcasting rules. In NumPy, Broadcasting refers to the set of rules that NumPy follows when performing operations on arrays of different shapes. It enables you to perform arithmetic operations between arrays that do not have the same shape but have compatible shapes. The code attempts to add two arrays of different shapes. According to broadcasting rules, the operation is invalid since the arrays do not satisfy the compatibility conditions for broadcasting. NumPy raises a value error because the shapes 3 and 2 are not compatible, as the trailing dimensions do not match, and neither is 1. Matrix operations.matmul. In NumPy, matrix operations are fundamental for linear algebra. Two key functions for matrix multiplication are np.dot and np.matmul, which can be used interchangeably in certain cases. However, np.matmul is more specific to matrix multiplication, and it prevents some operations that are allowed by np.dot, such as scalar multiplication. The code defines two 2x2 matrices A and B using NumPy arrays. np.dot.ab computes the dot product of the matrices, which is equivalent to matrix multiplication for 2D arrays. np.matmul.ab, on the other hand, performs matrix multiplication and is designed to be used with two-dimensional matrices. Both c.dot and c.matmul will result in the same output in this case, which is a new matrix with each element being the sum of the products of elements in the rows of A with the corresponding elements in the columns of B. Universal functions ufunc sqrt xp add. Universal functions, or ufuncs, are a key part of NumPy which provide the ability to perform fast element-wise operations on arrays. Common ufuncs include sqrt, xp, and add. These functions operate on ndarrays in an element-wise fashion, supporting array broadcasting, typecasting, and several other standard features. In the provided code, np.sqra computes the square root of each element in array A, result in 1.0, 2.0, 3.0, 4.0. The np.xpb function calculates the natural exponential, e to x, of each element in array B, leading to an array close to 2.718, 7.389, 20.085, 54.598. Finally, np.addab adds arrays A and B element-wise, resulting in 2, 6, 12, 20. These operations are performed quickly and efficiently due to the ufunc property of operating on an element-wise basis, which is a cornerstone of NumPy's capabilities for numerical computations. Aggregation functions sum, mean, median, std, var. Aggregation functions in NumPy are used to summarize the data present in an array by performing computations like sum, mean, median, standard deviation, st, and variance, var. These functions help to get a sense of data distribution within an array. The provided code snippet demonstrates the use of 5 common aggregation functions in NumPy. np.sum calculates the total sum of elements in the array. np.mean computes the average value. np.median finds the middle value when the elements are sorted. np.std calculates the standard deviation, which measures how spread out the values are. Lastly, np.var computes the variance, indicating the spread of the data's squared deviations from the mean. Basic indexing and slicing. Basic indexing in NumPy allows you to add individual elements or ranges of elements in an array. It's similar to how you'd access elements in a regular Python list. The code creates a one-dimensional NumPy array named R. The element at index 0 is accessed using R0, which is stored in first element. Similarly, R-1 accesses the last element of the array, which is stored in last element. Remember, in Python and NumPy, negative indexes start from the end of the array, with -1 being the last index. Advanced indexing Boolean integer arrays. In NumPy, advanced indexing allows you to access elements of an array more complexly than simple slicing. This includes using Boolean arrays to conditionally select elements and using integer arrays to select specific indices. The given code demonstrates 2 types of advanced indexing, Boolean and integer array indexing. In Boolean indexing, RR5, a Boolean array is created where each element states whether the corresponding element in R meets the condition. The resulting bool IDX is then used to select the elements in R that are greater than 5. Integer array indexing is shown by creating an array int IDX containing specific indices to be selected from R. The result int contains the elements at these specified positions, 1, 3, and 4, from the R array. Strides in slicing. In NumPy arrays, strides denote the number of bytes that should be skipped in memory to go to the next element. When slicing, the stride can be used to specify the step of the slice. This means rather than taking every element, the slice will take every nth element as specified by the stride. In the provided code, we first import NumPy and create a one-dimensional array with elements from 0 to 9, inclusive. Subsequently, we perform a slice operation on the array, R182. The slicing starts from index 1, goes up to index 8, exclusive, and selects every second element. As a result, sliced R contains the values 1, 3, 5, 7, effectively having a stride of 2, which skips every other element between the start and stop indices. Manipulating array shapes, ravel reshape transpose. In NumPy, shapes of arrays are essential as they define how data is organized in terms of rows, columns, and other dimensions. Common operations for manipulating shapes include ravel, reshape, and transpose. The provided code demonstrates 3 common operations to manipulate the shapes of a NumPy array. The ravel function flattens the array into a one-dimensional array without copying the data. The reshape function changes the array's shape to 2 rows and 6 columns, provided that the new shape is compatible with the total number of elements. The transpose function swaps the array's axes, effectively converting rows to columns and vice versa in a 2-dimensional array. Concatenating and splitting arrays. Concatenation refers to joining multiple arrays into one. In NumPy, this can be done using functions like np.concatenate, np.vstack, or np.hstack, depending on the dimensionality of the arrays. Using np.concatenate on array 1 and array 2 combines them into a single 1D array. The np.vstack vertical stack function stacks array 4 vertically onto array 3, effectively adding a new row to the 2D array. It's important for the arrays to have compatible shapes for the dimension along which they are being concatenated. Contiguous versus non-contiguous arrays. In NumPy, memory layout refers to how array elements are stored in memory. A contiguous array is one where the memory is allocated in a single, continuous block. Non-contiguous arrays may consist of scattered blocks of memory. Contiguity impacts performance and the efficiency of certain operations. The code above creates a contiguous array with elements of type int32. It then checks if the array is contiguous using the ccontiguous flag from NumPy's ndarray flags attribute. Afterwards, it creates a non-contiguous array by slicing the original array with a step of 2, which also skips memory locations. The contiguity of the resulting array is again checked using the ccontiguous flag. This flag will return false for non-contiguous arrays that do not occupy a single continuous block of memory. Copy and views in NumPy. In NumPy, data can be shared between arrays without copying the content. Understanding the concepts of copies and views is crucial for efficient memory management. A view is another way of looking at the data of the original array, whereas a copy creates a duplicate of the array and its data. The output illustrates how changes to the view affect the original array, because a view is just a different perspective of the same data. When we modify view array 0, original array changes as well. However, a change in copy array does not affect original array because the copy is a separate object with its own data. Deep copy versus shallow copy. In NumPy, understanding the difference between shallow copies, view, and deep copies is essential when manipulating arrays in order to avoid unintended side effects. Shallow copies create a new array object that looks at the same data, while deep copies create a completely new array with its own data. The provided code first demonstrates a shallow copy of a NumPy array using the .view method. Changing an element of shallow copy also changes the corresponding element in R, because both are referring to the same data memory. In contrast, a deep copy is created using the .copy method. Altering deep copy does not affect the original R, since deep copy has its own separate data memory. Reshaping arrays and memory order. In NumPy, reshaping an array means changing its shape without changing its data. By default, reshaping an array in NumPy is done in C order, meaning it will read and write elements using C-like index order, with the last axis index changing fastest. However, you can also reshape arrays in F Fortran-like order, where the first index changes the fastest. This can greatly affect performance, depending on the operation. The code shows how to reshape a 3x4 array into a 4x3 array using both the default C order and the F order. The reshaped C array retains the memory layout of the R, whereas reshaped F changes it to Fortran-like layout, which can be observed by the different positioning of the elements after reshaping. Understanding this is crucial, as certain operations might be faster on one memory layout than the other, depending on the sequence of elements you're working with. Reading and writing arrays to files. NumPy provides the save function to store a NumPy array to a binary file with a .npy extension. This format preserves the array's shape and data type. In this code snippet, we first import the NumPy library. Then we create a NumPy array named R, containing 3 integer elements. Using the np.save function, we then save R to a file named myarray.npy. The file is saved in the current directory unless a specific path is provided. Loading and saving with np-load.txt and np-save.txt. NumPy provides simple functions for saving and loading array data to and from text files. np.save.txt is used to write an array to a text file, and np.loadText is used to read an array from a text file. In this example, a 2x2 NumPy array is first created and then saved to a text file named savedarray.txt using n.saveTxt. The array is written in a plain text format with space-separated values by default. Afterwards, the same array is read from savedarray.txt into loaded array using np.loadTxt, reconstructing the original array from the text file contents. Binary file I/O with np-load and np-save. NumPy provides functions np.save and np.load to save and load array data to and from disk in binary format. This is efficient for storage and maintaining the precision of data. The code snippet demonstrates how to save an array to a binary file using np.save and load it back using np.load. First, we create an array data. We then save it to data.npy, where .npy is the default extension for binary files created by NumPy. Lastly, we load the data from data.npy into loaded data. The loaded data will be identical to the original data array. Matrix multiplication and the operator. Matrix multiplication in NumPy is performed using the np.dot function or the @ operator, both of which compute the dot product of 2 arrays. For 2D arrays, it's equivalent to matrix multiplication. It's crucial that the number of columns in the first matrix matches the number of rows in the second matrix. The code snippet imports NumPy and defines 2 2D arrays, matrices A and B. It then performs matrix multiplication in 2 different ways. C is the product of A and B using the @ operator, and D is the product of A and B using the np.dot function. Both C and D will result in the same matrix, showcasing that the @ operator is just syntactic sugar for the np.dot function when it comes to 2D arrays. Matrix decompositions, e.g. SVD. Eigendecomposition is a matrix factorization technique which decomposes a square matrix into eigenvectors and eigenvalues. Here is how we can do it using NumPy. In the code block, we import NumPy and create a square matrix A. Using the np.linaldaEAG function, we decompose the matrix into its eigenvalues and corresponding eigenvectors. The eigenvalues are the factors by which the eigenvectors are scaled during the transformation represented by A. Solving linear systems solve LSTSQ. To solve a linear system in the form of AX equals B, where A is a square matrix and B is a 1D array, NumPy provides the np.linal.solve function. When A is not square, or there are other reasons np.linal.solve can't be used, nplinal.lstsq can be utilized to find the least squares solution to AX equals B. In this example, we have a 2x2 matrix A and a vector B. The nplinal.solve function attempts to find an exact solution if possible. The np.d.lstsq function computes the least squares solution, which minimizes the Euclidean 2 norm B and xx2. The returned values from LSTSQ are the solution, xSTSQ, the sum of residuals, the effective rank of the matrix rank, and its singular values, S. Rcond equals none is specified to use the default cutoff ratio for small singular values. The inverse and pseudo-inverse in viv pin v. In linear algebra, the inverse of a matrix A is another matrix, typically denoted as A squares 1, that when multiplied with A, yields the identity matrix. The pseudo-inverse is a generalization of the inverse for matrices that may not be invertible or are not square. NumPy provides the inv function for computing the inverse of a square matrix, and the pinv function for computing the pseudo-inverse of any matrix. In the code example, np.linealg.inv is used to compute the inverse of a 2x2 matrix A. The result, A_inv, should fulfill the equation A_inv equals I, where I is the 2x2 identity matrix. However, since not all matrices are square or invertible, np.lineal.pinv is used to compute the pseudo-inverse of matrix B, which yields B_pinv. The pseudo-inverse provides a least squares solution to the equation B to x equals y, even when B is not invertible. Determinant and trace. The determinant is a scalar value that can be computed from the elements of a square matrix. In NumPy, you can calculate the determinant of a matrix using the numpy.linealg.dit function. This value can be interpreted in various ways, including as a measure of the matrix's invertibility. A non-zero determinant means the matrix is invertible. In the provided code, we start by importing the NumPy library. We then create a 2x2 square matrix A. To find the determinant of this matrix, we use the np.lineal.det function and pass our matrix A as the argument. The determinant is calculated and stored in the variable det_A, which is then printed out. The result will show the determinant of matrix A. Reshaping and resizing arrays. Reshaping an array in NumPy is a common operation where the shape of an existing array is changed without changing its data. This is often required in data manipulation tasks, where the structure of data needs to alter to fit the requirements of algorithms or other data structures. Firstly, we import the NumPy package under the alias np. We then create a 1D NumPy array called original array with numbers from 0 to 5 using np.arrange. Next, we reshape this array into a 2D array with 2 rows and 3 columns using the .reshape method, resulting in reshaped array. The total number of elements in the original array must match the product of the dimensions of the reshaped array. In this case, 6 elements fit perfectly into a 2x3 matrix. Adding and removing elements, append, insert, delete. Appending elements to a NumPy array means adding elements at the end of the array. It is important to note that append does not occur in place. A new array is returned with the appended elements. We import NumPy and create an array named R. We use np.append to add a list of elements 4, 5, 6 to the end of R. Appended R is then printed, which shows the result of the append operation. Combining and splitting arrays, concatenate vsplit hsplit. The concatenate function is used to join 2 or more arrays along an existing axis. In the provided code, 2 NumPy arrays A and B are concatenated along the first axis, rows. As a result, combined is an array that stacks A and B vertically. The output is a new array with shape 3, 2. Tiling arrays tile repeat. The np.tile function constructs a new array by repeating an array the number of times you specify. It is similar to laying down tiles. You start with one tile, the input array, and lay out copies to fill up a larger array space. In the code, we first import NumPy, then define our original array A with 3 elements. We use np.tile to create B by tiling A 2 times. The output B will be 1, 2, 3, 1, 2, 3, essentially repeating the original array twice in sequence, because we specified 2 as the repeat count. Understanding broadcasting rules. In NumPy, broadcasting allows arithmetic operations between arrays of different shapes by replicating elements in certain dimensions. To broadcast, dimensions of the arrays are compared starting from the trailing dimensions and working towards the leading dimensions. Broadcasting follows strict rules to determine if operations between 2 arrays are viable. In the provided code example, array A with shape 3 is broadcast to match array B's shape 3 or 1. Since the last dimension of A is the same as the last dimension of B, NumPy is able to broadcast A across B by replicating A's values along the missing dimension of B. Thus, A becomes an array of shape 1, 3 and is then broadcast to 3, 3 to match B. The result is element-wise addition between arrays of compatible shapes. Broadcasting with scalar values. Broadcasting in NumPy refers to the ability to perform operations on arrays of different shapes. When a scalar value is involved in an arithmetic operation with a NumPy array, broadcasting allows the scalar to be stretched across all elements of the array. In this code, we first import the NumPy library. Then we create a 1D array R with 3 elements. Next, we add the scalar value 10 to the array. NumPy broadcasts the scalar value 10 across the array adding 10 to each element, resulting in a new array result, where each element is the original value incremented by 10. Broadcasting with arrays of different shapes. Broadcasting in NumPy refers to the set of rules by which arrays of different shapes can be involved in arithmetic operations. The smaller array is broadcast across the larger array so that they have compatible shapes. In the code example, array A is of shape 3, which is a 1D array, and B is of shape 3, 1, a 2D array. According to NumPy broadcasting rules, array A is virtually replicated along the second dimension to match the shape of B. Then element-wise addition is performed between the arrays, resulting in a new array C of shape 3, 3. The final output would be an array with elements 11, 12, 13, 21, 22, 23, 31, 32, 33, where each value in array A has been added to the corresponding value in array B. Defining structured arrays. In NumPy, structured arrays allow you to define complex types where each element can be a combination of various subdata type components. This is useful for creating tabular data structures similar to those in databases, where each field can have a different type. In the provided code, we begin by importing NumPy. We then define a compound data type, dtype definition, where each tuple represents a field in the structure. For each field, we specify a name and a type. U10 is a Unicode string of maximum 10 characters, I4 is a 4-byte integer, and F4 is a 4-byte float. Next, we create the structured array with 2 records. Every entry in the array is a tuple that corresponds to the structure defined by dtype definition. Each element of the tuple corresponds to the data specified in the dtype. John's age is an integer 32, and his weight is a float 75.5, etc. Indexing structured arrays. To access elements within a structured array in NumPy, you use what is essentially similar to standard NumPy indexing, but you specify fields through their names. Let's create a simple structured array and access various parts of it. Firstly, we import NumPy and define the data type dtype for our structured array, including field names and types. Then we create the array items. Indexing with items name extracts all names. Items 1 gets the second record. Items price 0 gets the price of the first item. Nested dtypes and multidimensional fields. In NumPy, structured data types allow you to define complex types with fields that can be accessed similar to columns in a database table. Besides having simple fields, these data types can be nested by defining a structured type as a field within another structured type. Additionally, fields in structured arrays can also be multidimensional arrays themselves. The code defines a structured dtype with a nested dtype and a multidimensional field. The nested dtype contains simple fields for name and age, a multidimensional array field scores that stores floats in a 3x2 structure, and a nested field info, which itself is a structured type containing height and weight fields. A structured array records is then created with data that fits this complex structure. Finally, heights extracts the heights from the nested info field by indexing into records first with info and then height. The datetime64 and timedelta64 data types. NumPy's datetime64 data type allows the storage of date and time information as an array. It's especially useful for time series analysis or datetime operations. The code imports NumPy and creates an array with 2 dates specified in YYYMDD format. The dtype equals datetime64 tells NumPy to treat these as date-time values rather than strings. It prints the array containing datetime64 representations of the dates. Creating date ranges with nparrange. In NumPy, np.arrange function is commonly used to create arrays with evenly spaced values within a given interval. This function can also be used to create date ranges by specifying the data type as a datetime64 object. In the given code, np.arrange is used to generate a range of dates from April 1st, 2023 to April 7th, 2023. The dtype equals datetime64d parameter informs NumPy to treat the values as dates with a day precision. When printed, the resulting array contains a sequence of dates within the specified range, each a day apart from the next. Note that the end date 2023-0408 is not included in the resulting array. This is because np.arrange generates values up to, but not including the stop value. manipulating and formatting data arrays. To begin working with dates in NumPy, you need to understand how to create data arrays. NumPy provides the numpy.datetime664 data type, which enables us to create data arrays. In this example, we will create a simple array of dates. We imported NumPy and created an array dates using the np.array function. Each item in the list is a string representing a date, and the D type is specified as datetime64 to indicate that the array elements are date objects. When printed, the array shows the dates in the format YYY-MMDD. Memory mapping with np-memmap. NumPy's memmap is an array-like class that allows you to read-write large data files on disk without reading the entire file into memory. It's useful for working with large datasets, especially when the available RAM is insufficient. Memory-mapped files are not loaded all at once, but rather in small chunks as needed for operations, which makes them crucial for memory efficiency. The code creates a float32 memory-mapped file called mymemmap.dat with a shape of 1000 by 1000. The memmap array is then accessed and modified just like a regular NumPy array, with the first element set to 1.0. The flush method is called to ensure all changes are written to disk. The array is accessed again to print the first element, demonstrating that the data persists beyond the life of the mmap object. Finally, the mmap reference is deleted, which closes the memory-mapped file. Polynomials in NumPy. NumPy provides a submodule, numpy.polynomial, that allows for the manipulation of polynomials. For instance, using polynomials in NumPy, you can perform operations such as addition, subtraction, multiplication, division, evaluation at a point, finding roots, and fitting polynomials to a set of data points. In the provided code, we import NumPy and then define a second-degree polynomial with coefficients in the order of the constant term to the highest degree term, using numpy.polynomial.polynomial. The polynomial represented here is x2 minus 4. We then evaluate the polynomial at x equals 2 using the class instance like a function. Lastly, we calculate the roots of the polynomial, the values of x for which the polynomial equals 0, using the roots method. Using histogram functions, histogram dd, NumPy provides powerful functions to compute histograms that categorize data into discrete bins. np.histogram is used for computing histograms for one-dimensional data, and np.histogramdd is for multidimensional data. Let's look at how to use these functions with an example. In the code, np.histogram bins the random data into 10 equally spaced bins and returns 2 arrays. Hist contains the counts per bin, bin edges contains the edges of the bins. The np.histogramdd function is used for 2D data stored in points, and also creates a 10 by 10 histogram, ndarray, with edges giving the bin edges for each dimension. Vectorizing functions with np-vectorize. In NumPy, vectorization is a powerful concept that allows for element-wise operations on arrays without explicitly writing loop constructs. It leads to faster execution and more readable code. Sometimes you may have complex operations or functions not natively supported by NumPy's vectorized functions. In such cases, you can use np.vectorize to apply your own Python function across all elements of an array. The provided code demonstrates how to use np.vectorize to transform a function that is intended for scalar inputs into one that can operate over NumPy arrays. First, we define a simple Python function, scalar computation, that performs different calculations based on whether a number is even or odd. By applying np.vectorize to this function, we create a new function, vectorized computation, which can then be called with a NumPy array r as an argument. When vectorized computation r is called, the original scalar computation function is applied to each element of r, resulting in a new array where the computation has been applied element-wise. Applying user-defined functions with applyAlongAxis. The numpy.applyAlongAxis function allows users to apply a custom-defined function to 1D slices of an array along a specified axis. By defining a function that operates on a 1D array, and then applying it with applyAlongAxis, one can perform operations that are not covered by built-in NumPy functions. This can be particularly helpful when you have complex calculations that need to be vectorized for efficiency. In the given code, myfunc is defined as a function that checks whether all elements in its input, a 1D array, are less than 100. The np.applyAlongAxis function is then used twice. First, it applies myfunc along the 0th axis of R, which means the function is performed on each column, resulting in a 1D array indicating whether each column in R passes the check. The second application checks each row by setting the axis parameter to 1, generating a 1D array that shows whether each row in R passes the check. Both result and result rows will show arrays of Boolean values indicating the check for each column and row respectively. Building custom ufuncs with NP from Pyfunc. In NumPy, universal functions, ufuncs, are instances of the numpy.ufunc class. They operate element-wise on an ndarray. Sometimes you may need a function that operates on arrays in an element-wise fashion, but can't find an existing NumPy function that accomplishes what you need. In such situations, np.fromPyfunc allows you to create your own ufunc. np.fromPyfunc takes an arbitrary Python function and converts it into a ufunc. Keep in mind that ufuncs created with np.fromPyfunc operate at Python speed, not C speed, which is normally slower. The code showcases how to create a custom ufunc. The myCustom function defines the operation to be vectorized, x to 2 plus 3, x plus 5. Then, np.fromPyfunc is used to create a ufunc, myUfunc, that accepts one input and returns one output. The input array is a simple NumPy array with the values 1, 2, 3, 4. Applying myUfunc to input array yields result array by element-wise, applying myCustom function to each value in the input array. Understanding memory alignment and stride tricks. Memory alignment refers to how the bytes of an array's data are arranged in memory, which can affect performance due to hardware constraints. Stride tricks involve manipulating the strides attribute of a NumPy array to change how one accesses array elements without copying data, which can enhance performance and enable efficient array operations. In the provided code, aligned array is created with align equals true, ensuring that the memory is aligned according to the data type's natural alignment, which could lead to better performance on some hardware. Then, using np.lib.stridetricks.astrided, we create subsampled array that is a view of every third element in aligned array. The strides parameter is set to skip over 2 elements. Each float64 type takes up 8 bytes, hence item size to 3. This does not copy the data, but provides a new way to access the data, which can be very efficient for large arrays. Profiling and timing code. Understanding the performance of your code is crucial for writing efficient numerical computations. Profiling and timing techniques allow you to identify bottlenecks and optimize your code accordingly. Python provides several tools to help you measure and analyze the performance of your code. In the provided code, we first import NumPy and the time module. We define a function sumArray that uses NumPy to sum the elements of an array. We then create a large array of random values and time the execution of the sumArray function with this array. The time.time function is called before and after the execution of sumArray to measure the elapsed time in seconds. Finally, we print the time taken to perform the sum. This simple technique is often sufficient for quick, informal benchmarks. Efficient use of array expressions. NumPy is optimized for vector operations, which means that operations on arrays can be executed without explicit loops. This not only leads to more readable code, but also to significant performance improvements because the loop runs at C-level speed inside NumPy, rather than at Python interpreter speed. In the code, 2 arrays A and B are created and operations are performed on them using array expressions. Using A plus B, rather than iterating over each element for addition, and A star B for element-wise multiplication, utilizes NumPy's broadcasting abilities, leading to more performant code. These operations are internally optimized, making full use of the underlying C libraries and hardware capabilities. Using numXBar for fast numerical expression evaluation. numXBar is a fast numerical expression evaluator for NumPy. It allows element-wise operations to be performed quicker by using a just-in-time JIT compilation. numXBar evaluates the expression in chunks, which reduces memory usage, and utilizes multiple cores, which can boost computational speed. In this code snippet, we import NumPy and numXBar. We create 2 NumPy arrays A and B. We then use numXBar's evaluate function to compute the expression A plus B 2. NumExpr evaluates this expression faster than if we performed the same operation directly with NumPy, especially for large arrays, because it optimizes the execution by using efficient threading and memory management.